Tonight, we want to report on one of the most unnerving discoveries in space science. Most of the universe is missing.
Stranger still, wherever and whatever this missing stuff is, it controls the fate of the cosmos. Welcome to the invisible universe.
We're here at the Mullard Radio Astronomy Observatory in Cambridge. These amazing dishes are at the forefront of one of the strangest and yet most important searches in science, the quest to understand the invisible universe. We live in a world made of matter. This radio telescope is matter. So are the planets, the stars, and interstellar dust. So you might think it's easy stuff to find, but it turns out that even this ordinary matter is almost invisible. And that's only the start. As well as ordinary matter, there's another kind of matter we think is out there, but we've never actually seen. We call it dark matter. Chris visits the largest dark matter detector in the world to try and find it.
And Jim El-Khalili investigates the most puzzling mystery, so mysterious that almost all we know about it is a name.
Dark energy.
Tonight, we'll guide you through this mind-boggling invisible universe and show you how it could control the fate of the entire cosmos. We start our journey with a success story, ordinary matter.
That's what's called baryonic matter. And the thing is that when you add up all the baryonic matter in the universe, all the stars, the galaxies, the black holes, the planets, the gas, the dust, everything, you find you come up very short.
We just can't find enough of the stuff, given what we know about the early universe.
But where is this missing matter?
In the last few months, it may finally have turned up. To find out where it was hiding, Maggie met up with Amélie Sontange.
Amélie, how do we know that there's stuff missing in the universe?
To figure out how much baryonic matter there is in the universe, we can look at the cosmic microwave background. And the cosmic microwave background is an image of the universe as it was about 400,000 years after the Big Bang.
So it's quite granular. What's that all about?
The difference between the red spots and the blue spots is very, very small temperature fluctuations across the entire sky.
So what do the temperature fluctuations in this picture mean?
Well, there is a lot of information in this. We need to find these temperature variations, measure their position, the distance between them. And then we compare that with our cosmological models. And we can infer how much baryonic matter there was in this soup of baryons and photons.
So that was the universe in the past. What are we observing now?
So now we can go and use our telescopes to look at the galaxies around us. And with that, we can measure their stars, the gas, the dust between the stars. And if we add all of that up, we come up to about 10% of the total that is inferred by the cosmic microwave background. So there's about a 90% gap there.
Yeah, so 90% is missing, it's not visible.
That's right.
Aha.
So now we had to be a bit clever about that and try to go and find that extra missing mass. We assume a lot of it must be in gas that is located around galaxies. But how do we measure this thing? Big question. So I have a little demo here we can do to illustrate this. So I'm going to spray some water, which presumably you can't really see. Right?
Not really,
it's just
no.
vapor. But what about if I take this and shine a light from the background?
Oh yes, I
All
can
of a
see it now.
sudden, we can see the mist appear.
So then what are you using as your torch?
So we can use as torch what we call quasars, supermassive black holes in very distant galaxies that are very, very bright. They are or cosmic torches in some sense.
Yes.
And by looking at their light, we can see some of the light being absorbed by the low density gas in front of it.
So how much of this gas does this account for? Does it mop up the 90% that's missing?
Not quite. So if we combine all of this, all the different observations, we come up to about 70%.
Okay.
So there was still the 30% of what we call the missing baryons that were not accounted for. So it's been suspected for a long time that these missing baryons must be hiding at temperatures of about 1 million degrees.
That sounds hot.
It is hot. It's a very difficult temperature. If it were slightly hotter, we would be able to observe it directly by X-ray light it would produce. If it were slightly colder, slightly denser, we could apply our technique here with a flashlight to be able to see it. 1 million Kelvin is just in a bit of a no man's land where we don't have easy ways of detecting it.
But where is this hot gas? Scientists guessed that it lay in invisible gassy threads called filaments that occupy the space between galaxies. And they came up with an ingenious way of seeing them, using the cosmic microwave background.
So what some astronomers have done now is use some data from the Planck satellite to look for this gas in filaments in between galaxies. Now, each filament between galaxies is very diffuse. There is trace amounts of gas in there, so we are not going to be able to see it directly. We need to find a trick to boost that signal. We see light from the cosmic microwave background, these photons that are propagating, and when they hit the filaments of warm gas, the photons are scattered, they change direction slightly, and they lose a little bit of energy. So we can pick up on these energy changes.
This image shows the new result, the invisible filaments between the galaxies, now rendered visible, using light from the beginning of the universe.
So this is the filament here.
Yes.
So what's our view of the universe now? How does it all add up?
With this discovery, we think that we have located all the baryons in the universe today, which is great news. It's great because it confirms our models and it gives us a good view of where the matter is in the universe.
That's an amazing result. Thank you so much for coming and sharing it with us.
Pleasure.
So that's one part of the invisible universe we're finally able to see. But not all invisible matter is that easy to identify.
Here at the MRAO in Cambridge, telescopes like these peer deeper and deeper into space, producing ever more detailed information about what's out there in our universe.
And they're uncovering new clues about a very different kind of invisible matter. One that dwarfs ordinary matter in mass and seems to shape how the whole of the cosmos is held together.
I'm talking about the mystery of dark matter.
We think that dark matter exists because of some strange phenomena we've observed. Some of the first evidence came in from studying distant galaxies and how they rotate. Now, it's not a strictly accurate analogy, but imagine this turntable is a distant galaxy.
As the turntable spins, the marble will fly off. With galaxies, a similar thing should happen. As they rotate, the stars within them should fly off into deep space. But they don't. It appears that gravity keeps them in place. But the problem is, there simply isn't enough mass visible in the galaxy to produce this much gravity. Something else must be providing this extra gravity to hold the stars in place.
So scientists came up with the idea of dark matter, a substance that has mass, so affects the gravity, and holds the galaxy together.
They suspect dark matter is made of heavy subatomic particles, affected by gravity, but little else, making it totally invisible.
So, what is dark matter? And how do we go about finding it?
Chris went to visit one of the biggest dark matter laboratories in the world.
This is a wonderful place to be this time of year. Gran Sasso in the heart of the Italian Apennines. But we're not here to admire the view, we're heading underground in search of dark matter. This laboratory isn't up in the mountains because of the clear air, it's actually underground. And that's because we need to shield ourselves from cosmic rays, particles that are raining down on us all the time. And so out here, we're being hit by them every second, but once we go into the tunnel, disappear underground, where the laboratory is, we get 1 million times fewer. That means we can see the more subtle signals that we're looking for, so dark matter and other cosmic particles. This is amazing. We're driving down a secret tunnel underneath a mountain, just like in a James Bond film. But this is where physics gets done.
I'm here to meet Rani Budnik, scientist on Xenon 1, a detector designed to find the most elusive particles in the universe.
This is the Xenon experiment.
This is amazing. This place is enormous.
Yeah, it's really large, spacious.
I reckon if you got somebody to design what they think a physics experiment would look like,
Yeah,
this is pretty close.
Here, deep under the mountain itself, the detector is shielded from cosmic rays and from surface radiation. But dark matter should pass right through.
We have 1,400 meters of rock just to protect us from the universe,
Okay.
which is barely enough.
Okay.
The detector itself is 3.5 tons of the inert gas xenon, held within this huge tank. The hope is that dark matter is made of WIMPs, weakly interacting massive particles, which will pass straight through the mountain, but then just occasionally score a rare direct hit on a xenon nucleus, which Rani should be able to detect.
What do we know about dark matter?
We don't know much about what this particle could do, but we do know many things about what it cannot do. So we know it doesn't interact strongly with light or with any matter that we know.
So this is a problem because you're trying to detect it. So how on earth do you build a dark matter detector?
You need to look for a very rare interaction. If the interaction strength is very, very weak, that means that they do interact, but rarely.
When you say interact, what should I be imagining? What's actually happening?
What we're looking for is basically kind of a billiard ball interaction. They just knock something, and then our particles, the normal particle, is knocked. And then this particle gets some energy. Our nucleus, our xenon nucleus, basically is being kicked. And then the xenon nucleus deposits the energy inside our detector.
Okay, so you're looking for these direct hits.
Exactly.
These rare cases when a dark matter particle happens to hit directly a xenon nucleus.
Yes.
And how often do we think that happens?
So we know that in this detector, in Xenon 1 ton, we expect at most, let's say, in a low number of tens of events per year.
If you see a signal, what will it tell us?
We're going to see, if we see something, there would be a bunch of events, let's say around 5, that are consistent with being dark matter and, more importantly, very inconsistent with being anything normal that we do expect to see in the experiment.
Well, that's the cheerful possibility. You could press the button and see nothing.
Exactly. That's actually what usually happens, or what happened all the time so far.
So what does that tell us?
Each time we look at data, and that happened in the past, and don't find anything, that means we can rule out. We can just send them back to the drawing board and look for explanations on what could be dark matter that is not seen by our experiment and by other experiments.
Well, whatever the results are, I hope you'll come back and tell us about them. Thank you very much.
You're welcome.
It's wonderful to be here and genuinely exciting to see these marvelous experiments in action. But with all this effort, they still haven't found anything. And that makes me wonder, why are astronomers so sure that particle physicists haven't found dark matter? What is it that makes astronomers so convinced that it exists?
We've been able to take pictures of the universe when it was very young using specialist telescopes that just look back through time by looking to extraordinarily large distances.
So this is the cosmic microwave background.
The cosmic microwave background, exactly. And people had predictions for what that should look like long before detailed observations were actually technologically possible. And those predictions are based on a kind of competition. There's a competition between gravity pulling stuff together and pressure pushing things apart. That's going to give rise to kind of ripples going through the early universe. And what we're able to do using these satellite pictures is to actually measure how strong are the ripples as a function of scale. So you can have a look at how ripply the universe is on, say, small scales versus how ripply it is on large scales. And depending on how that balance between gravity and pressure plays out, that gives you a very distinctive set of patterns.
So these patterns tell you that the dark matter exists?
The more dark matter you have, the more there's a sort of tendency to make big ripples. And the more you have of normal matter, the more pressure there is that's able to resist that.
And so we get the right amount of dark matter?
Yeah, we get the right amount of dark matter based on the entire universe, and that's a genuine prediction coming from dark matter theory.
So if the detectors aren't sensitive enough to find the dark matter, is there a point we get to where we should be worried, where a non-detection would start to question what we know from looking at the universe?
There's certainly a point coming up where we should start to worry about our simplest and, in a sense, most compelling explanation of what particle is responsible for dark matter. These are the so-called WIMPs, or weakly interacting massive particles. And there's a very natural sort of set of expectations for how big and sensitive a detector you need to build before you'll be able to find it. And we are actually reaching that kind of level of sensitivity, and so far, of course, haven't found anything. So in the next few years, at least as far as that sort of simplest and most favoured explanation for what dark matter actually is, we should start to get a bit concerned if we don't hear anything pretty soon.
Well, there's lots more to do either way. Andrew, thank you very much.
Dark matter is, of course, as invisible to the amateur as it is to the professional. But anyone can look up and glimpse objects in the night sky that tell us about this elusive material. Pete Lawrence takes a look at a few of the objects that fascinate dark matter scientists. And he shows us how photography can help us see more.
The idea of the invisible universe isn't really news to the amateur astronomer. We make the invisible visible every time we use our telescopes to look at the stars.
Take, for example, the Andromeda Galaxy. It's between the constellation of Cassiopeia and Andromeda, just up from the star Merak.
So what at first appears to be just a faint, fuzzy, elongated blob, with a telescope is revealed to be something far more complex.
It's a spiral galaxy made up of an estimated 1 trillion stars and huge clouds of gas, all revolving around a supermassive black hole.
We now believe the shape is due to dark matter, which infuses the galaxy, holding the stars in position through gravity. Spiral galaxies like Andromeda are interesting for other reasons too. Now, I managed to get a very quick photograph of it just now through a gap in the clouds. And if you look at the shot, you can see there's a little star-like dot very close to the center of the main Andromeda galaxy. Now, that's not a star, that's actually a dwarf galaxy, which is in orbit around the main galaxy. These satellite galaxies are fascinating for astronomers because they're thought to contain proportionally more dark matter than the larger galaxies. They're a bit of a puzzle too, because if current theories on dark matter are correct, we should be seeing more of them than we've so far found. There are other dwarf galaxies out there too, which you can try and photograph.
At this time of year, there's a wonderful dwarf galaxy visible to a camera in the constellation of Leo. It's close to the bright star Regulus and is called Leo 1.
Now, the length of exposure you need to use will depend on the quality of your skies. If you use a long exposure under light-polluted skies, the image will come out just pure orange, so you then need to knock it back a little bit. Now, the longer your exposure, the more influence you're going to get from the rotation of the Earth, so the more star trailing you will have on a fixed platform. So then you may need to consider going to a tracking platform like I've got here.
And here's one final example of how to use photography to make the invisible visible. Nothing to do with dark matter, but it's
Website, and we'll show you how to find some of them. And if you do get any photos, don't forget to add them to our Flickr page, because we'd love to see them.
As we explore the invisible universe, we finally come to our most problematic mystery.
It seems there's something else we need to explain, something we know very little about, but which might control the entire fate of the universe. Jim Al-Khalili explains.
Take a moment to consider what astronomy and physics have achieved. Sitting on our small rock in an unremarkable part of an apparently unimportant galaxy, we've looked out and seen back to the very beginning of time.
We've peered into the furthest corners of the universe, and we've uncovered the fundamental laws that govern the behavior of energy and matter. And yet, there is a problem, a big puzzle that remains unsolved.
Let me first explain why this puzzle even exists. See what happens when I throw a stone into the water.
The ripples spread outwards at a constant speed.
Now, consider matter moving outwards from the Big Bang. Imagine, hypothetically of course, that we could switch off the force of gravity.
Then, with nothing out there to slow them down, all the galaxies should move away from each other at a constant speed, just like the ripples. But in reality, gravity from their combined mass slows down the expansion.
We now know how much normal matter there is in the universe, and we have a good idea how much dark matter there is out there too. So we should know how the gravity of all this stuff influences the way the universe is expanding. And at this point in its evolution, our calculations suggest that this expansion should be slowing down, but very slowly. However, astronomers have discovered that this isn't the case.
To get a sense of how we know this and why it's a problem, I've come to the Rawlings Array at the Chilbolton Observatory.
In August last year, this was one of the many radio telescopes around the world that observed the biggest astronomical event of 2017.
Deep in space, two neutron stars collided, causing a stellar explosion of incredible violence. This so-called kilonova unleashed a massive burst of gamma rays and a powerful gravitational wave, both of which were measured here on Earth. Scientists have now used this event to measure the expansion of the universe. This is how. The gravitational wave told them how much energy the kilonova produced and how far away it was. They also worked out from the gamma rays how fast the galaxy was moving by measuring their redshift.
So we now have a measure of how far away the kilonova was when it exploded and how fast it was moving. So here's the $64 million question.
Would this galaxy move at the speed they just measured if gravity were the only force acting on it?
And here are the results. Obviously, I'm ignoring lots of subtleties and complexities, but the speed, if gravity were the only influence, would be this, 1,600 kilometers per second. But the speed, according to the neutron star collision measurement, is this, 3,000 kilometers per second, almost double. Now, these two numbers are different, very different.
It's more evidence for a startling conclusion.
The universe's expansion can't be slowing down. In fact, it's speeding up.
So, if the universe is expanding faster and faster, what's making it accelerate?
Well, the truth is, we don't know. But at least we've given it a name. Dark energy. A weird new force that pushes the universe faster and faster. This is the ultimate invisible something in the universe, because there has to be a hell of a lot of it out there, somewhere. And all this matters because dark energy could be the key to explaining how the universe will end. Without dark energy, gravity is the most significant force dictating the fate of the universe.
If gravity is the dominant force, then it means that one day the universe might stop expanding and start contracting. Eventually, it'll collapse together in what's known as the Big Crunch.
But if dark energy turns out to dominate, then the end of the universe could be much lonelier. As the universe spreads out, the influence of gravity becomes weaker until everything's too far apart for it to have any effect. Then, dark energy will be the only player in town.
As dark energy keeps pushing the universe apart, eventually all galaxies will move so far away they'll become invisible to each other. The distances between them will become so great that light from one would never reach the others, and the universe will disappear into darkness forever.
A sobering thought. So there's a lot to play for over the next few years, but don't panic. None of this is due for another 20 billion years or more. And who knows, it may all turn out to be wrong anyway.
That's it for this month, but do join us for the next programme.
Meanwhile, don't forget to check out the website with Pete's Star Guide, our special weather forecast, and all the extra material that we just couldn't fit into the programme.
In the meantime, of course, get outside and get looking up.
Good night.
More from Professor Jim Al-Khalili on Radio 4 on Tuesday morning as he talks about his ultra-cheap computer for teaching children. The Life Scientific is at 9. Tomorrow night we're heading for the Highlands, Scotland's wild heart, here on BBC4 at 8.